So we're still in the process of building up to thermodynamics. Last time we started talking about calorimetry, and for understanding calorimetry, really the key, I think, is understanding this this graph, this figure. So if you have temperature of a gas on the vertical axis, and you have internal energy of the gas on the horizontal axis, then if you start out at some arbitrary place, I guess temperature, if we think of this in Kelvin, then it's going to start somewhere above 0. If you think of it in Celsius, it's going to start. So yeah, let's do it in degrees Celsius. So let's say that it starts out in the solid phase. What is the part going to look like where you're adding energy to a solid material? Is it going to look like a clover shape, or it's going to be a line? It's going to have some slope to it, so it won't be horizontal yet. Okay, this is a solid. Until it reaches some point that is the phase change temperature. So this is the liquid solid boundary. And what's it going to do as soon as the temperature, as soon as you add enough internal energy that the temperature gets up to the liquid solid boundary, what's going to happen when you start adding energy now? It's going to be flat now. And in this region, it's a mixture of liquid and solid. How much liquid and how much solid is determined by how far you are along this piece. So this is a liquid solid mixture. When you're over here, you have almost all solid with just a little bit of liquid. When you're here, you have half liquid, half solid. When you're here, you are almost all the way to liquid. And finally, when everything has become a liquid, then you start ramping up again. How much energy is this? Well, the amount of energy between this point and this point is equal to the mass of the material you have times its latent heat. And this is called the heat of fusion. Now at this point, it's all liquid, and the temperature is increasing until you get up to a new boundary point, and that is the gas liquid boundary. And if you add more energy here, you get more and more of the material changing from a liquid to a gas. So if you're near this endpoint, you have mostly liquid at that phase change temperature and a little bit of vapor. If you get here, you have mostly vapor and a little bit of liquid. This amount of energy is the mass times the latent heat of vaporization. And then as you increase the temperature more, or as you add more energy to it, you just get all gas and its temperature is increasing. And I started off by doing a calorimetry problem. Without phase change. So remember, the key to, like, the main equation, the underlying principle for calorimetry is any heat you add to one body in the isolated system plus the heat added to another body, and then if you have more than two materials, you keep adding and adding, has to equal 0. It's a conservation of energy thing. So energy is conserved in an isolated system. And without phase change, Q is equal to the mass times the specific heat for that material times the change in temperature. And another way you can think of that is mass times the specific heat times the final temperature minus the initial temperature. Okay, so the calorimetry equation then ends up saying the mass of the first material times its specific heat times T final minus the initial temperature of that first material plus the mass of the second material times its specific heat times the final temperature minus the initial temperature of the second material is equal to 0. Let's say the two materials must be isolated for this to hold. Heat. I guess let's just step back for a second. And so internal energy, does anyone remember what the definition of internal energy is? What's the internal energy of a gas? 40? Maybe. Depends on the gas. So the internal energy is the total kinetic energy of all the molecules. Okay? And there are multiple ways that you can increase the energy. You know, I mean, you've seen conservation of energy equations before. There's a lot of different ways energy can be expressed. So there's a lot of ways you can add energy to something. You can do work on the material. You can increase its potential energy and, you know, let the potential energy act on it. But if you have an isovolumetric process, okay, so any of those things where you're adding, taking energy from one thing to another, that's called a process, okay? If that process is isovolumetric, that means you're not applying any forces to anything. You're not lifting it up. You're not compressing it. And in an isovolumetric process, the only way to change internal energy is adding or removing heat, okay? And so in this section, changes in internal energy are only going to come about through heat. When we start talking about thermodynamics, we're going to add other ways to change the internal energy. Okay, so I did one problem last time this way. I'd like you to work on a problem, phase change, calorimetry without phase change. You can look back at your notes, talk to each other about it, just see if you can work your way through it. So say that 0.1 kilograms of solid iron at 5 degrees Celsius is dropped into an insulated cup of 0.5 kilograms of water at 20 degrees Celsius. What's the equilibrium temperature of the system? Well, when you see a problem like this, the first question, I guess, is how do you know that there's not going to be a phase change? Well, in this case, the liquid solid boundary of water, the freezing point, and this is at standard pressure, is 0 degrees Celsius. And the vapor liquid boundary of water is 100 degrees Celsius. Okay, so the water is already between these two. So, you know, the water is a liquid because it's between these two temperatures. And you're putting something in that's also between those two temperatures. The only way for energy to be exchanged through heat is if there's a difference in temperatures. And so those are going to find a final temperature somewhere between those two, okay? All the temperatures between these two keep the water at liquid, so there's not going to be a phase change. And the boundaries of iron are, you know, much, much higher. So, okay, so take a few minutes and see if you can work through that one. Feel free to look back at your notes, talk to each other, and ask me questions if you get stuck. Yes, you do. So, yes, the specific heat of iron is 450 joules per kilogram Kelvin. And for liquid water, C is equal to 4186 joules per kilogram Kelvin.